This is your third and final installment for Chapter 15. And in this video, we'll be talking about Le Chatelier's principle, which is tied into the reaction quotient, which is Q. And we're going to talk about ICE tables, the infamous ICE tables. So just to get going, Le Chatelier's principle is what we're going to start with. And the basic idea of Le Chatelier's principle is that if you disturb an equilibrium, it will shift to reestablish itself. Okay, so that means that if I change the amounts of reactants or products or the amount of heat or the amount of pressure, the equilibrium will respond by making either more reactants or more products in order to reestablish its equilibrium. Okay, and for a long time as a student, I had a hard time figuring out whether the reaction would shift left or shift right, or what the effects of changing the equilibrium would have. And surprisingly, it wasn't until grad school when a fellow grad student gave me an idea that sort of cemented it all for me, and it's a surprisingly simple idea. And the easiest way to envision Le Chatelier's principle is with a ball rolling down the hill. Okay, and you're like, what? What does that have to do with chemistry? And well, here's the visualization. Is that if I have an equilibrium, reactants in equilibrium with products. Now imagine that we have a plank of wood sitting on top of that balance, that equilibrium. And right in the center of that, we have a ball. Okay, so if I change the amount of reactants or products, I'm going to tilt that plank one direction or the other. Okay, so let's imagine if I were to increase reactants. Okay, let's say I've established an equilibrium, and once that equilibrium is reached, I add more reactant to the scenario. What I'm going to do is I'm going to push up on this side of the plank. So instead of having a nice balanced plank, now my plank is tilted in this direction, and the ball rolls downhill. And so if I increase reactants, I shift right. The direction the ball will roll tells me which direction the reaction will shift. So it shifts right to make more products. Okay, and it will make more products until that equilibrium balances out again. So what happens if I, instead of increasing reactants, let's say I decrease reactants? Okay, let's say I take some reactants away. What I'm going to do is pull down on this side of the equation, and so that tilts my plank in the other direction, and my ball still rolls downhill. Okay? So if I decrease reactants, I shift left. And so it will respond by making more reactants. Okay, the equilibrium wants to have itself balanced out. Okay, so what happens if I add more products? Right? Same situation as if I added reactants. I'm going to push up on this side of the plank. My plank will tilt this direction, and the ball rolls downhill. Okay, so if I increase products, I shift left to make more reactants. And I do apologize, once again, I'm probably going to do this every video for my handwriting. It seems to be especially rough today. All right, so last scenario, let's say I decrease products. I'm going to pull down on the product side. So my plank gets tilted that direction. And the ball rolls towards more products. So we shift right. To make more products. Okay. Now, heat can be a factor in shifting equilibrium. So let's say, instead of just saying reactants and products, let's put an actual reaction on the board here. So if I have my ammonia production reaction, which is an equilibrium, and this is an exothermic reaction, so I would have a delta H reaction equal to negative 92 kilojoules per mole. Okay, that negative sign, remember, that should be a triangle, delta H. So the negative sign on delta H means that this is exothermic, right? That means that heat is a product. Okay, and this is a very important aspect of things. If it's an endothermic, then we have to put heat in, and heat becomes a reactant. Okay, so if I were to consider heat as a product, I could actually put it in to my equation as a product. Okay, so if it were an endothermic reaction, I would include it on the left side of the equation as a reactant. But if it's exothermic, heat is a product, so I can consider that as a product in my reaction. So if I add heat to my reaction, so if I heat my reaction up, I'm going to push up on this side of the reaction. That's going to shift my equilibrium. So if I'm pushing up on the product side, that's going to shift my plank up on the right side, and my ball rolls downhill. Okay, so exothermic, adding heat, we shift left. Okay, if I remove heat, let's make sure that I label this so that this is clear in the notes. This is for exothermic. Okay, if I remove heat, that's the same thing as pulling down on the right side. My plank will shift in this direction, and the ball rolls to shift right. Okay, so exothermic reactions, we put heat as a product, and then we can treat Le Chatelier's principle exactly the same as we would for any of the components. Okay, endothermic, let's do a generic endothermic because I don't have that prepared. Let's say A plus B in equilibrium with C, and let's say delta H is, I'm just going to throw out a number, negative 50. Excuse me, positive 50. Okay, that means that we are endothermic. So heat is a reactant. Okay, so I could rewrite my equation and say heat plus A and B in equilibrium with C. So if I add heat, that shifts my plank up on the left side, and my ball rolls downhill. We shift right. Okay, so heat can be a component just like any of the reactants and products, right? You just have to make sure that depending on whether it's endothermic or exothermic, you have to put heat on the correct side of the equation. Now looking back here at my ammonia reaction, so the production of ammonia is an extremely important industrial process. Ammonia is one of the top, the most used chemicals in the world. And so production of ammonia is very, very important. The problem is that even though formation of ammonia from nitrogen and hydrogen is technically a spontaneous process, it's a very, 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 very slow process. Okay, so one of the ways that they go about trying to speed up the reaction, and we learned about this in chapter 14, heating up reactions is a common way to make them go faster, right? So to speed up the reaction, add more heat. Well, with our ammonia equation here, if I add heat, my equilibrium shifts to make more reactants instead of making more ammonia. So I'm speeding the reaction up, but I'm actually getting less ammonia out of it. Here's the way that we go about dealing with that. We change the pressure. Okay, so pressure changes in equilibrium are a little different. Okay, so if we increase pressure, we shift to the side with fewer moles. Come on, pencil. Okay, so looking back at our ammonia reaction, okay, so on the left side of the equation, I have a total of 4 moles. 4 moles of gas, right? And the fact that it's gas is important. Let me put that up in here, fewer gas moles, okay? And on the right-hand side of the equation, I have 2 moles of gas. Okay, so if I increase pressure, we shift right. Okay, so we shift to the side with fewer moles of gas. Okay, it's kind of like, I always imagine it sort of like squeezing a balloon. If you squeeze one side of a balloon, all the air moves to one side. Pressure changes to equilibrium are kind of the same way. So on the right-hand side, we have more, you can imagine that we have more space because there were fewer moles there, right? So if we increase the pressure, it's going to shift to the side with fewer moles. Okay. Now, another important aspect is the way we increase pressure is by decreasing volume. Okay, that's a very important aspect. Because if I increase pressure by adding an inert gas, for example, to my reaction vessel, there is no effect. Okay, now let's talk about that. So with our ammonia production, we said that if we want to speed up the reaction, we heat it up. But if we heat it up, then the equilibrium shifts towards fewer moles of ammonia. So in order to to speed up the reaction and shift the equilibrium towards more products, we increase the pressure of the reaction. Okay? So ammonia production plants they operate on very high temperatures and high pressures. And additionally, to increase the production of ammonia, they add a catalyst, and we'll talk about that here in just a second. So changing pressure by decreasing volume, we will shift our reaction towards fewer moles of gas. Okay, fewer gas moles. Okay, but adding an inert gas no effect on equilibrium. Okay. The reason for that is that the inert gas doesn't change the partial pressures. Doesn't change the ratio of partial pressures, to be specific. Okay, so the ratios of reactants and products, as far as their partial pressures are concerned, doesn't change. So if we're not changing the ratios of partial pressures, we're not affecting the equilibrium. Okay, so this is part of your evaluation of equilibrium. So understanding how changes in concentration affect equilibrium, understanding how changes of pressure affect equilibrium, and adding inert gas. How does that affect equilibrium? And in fact, it doesn't. Okay. So the last aspect of talking about this is adding a catalyst. Okay. A catalyst speeds up a reaction, right? Talked about that in the last chapter. Right, so speeding up a reaction, we reach equilibrium faster. But it doesn't affect the equilibrium itself. All right, we reach the same equilibrium if we add a catalyst. We just get there faster. Okay, but the equilibrium itself is not affected. We don't shift one way or the other by adding a catalyst. Okay, so that little piece there is important. Okay, so why are we talking about shifts in equilibrium? Okay, so that leads us into our next topic, which is the reaction quotient. the reaction quotient is represented by capital Q. Okay, so reaction quotient is basically a snapshot of reaction progress. Okay, so we have some reactants and some products. Are they at equilibrium yet? Okay, so we can start a reaction even by putting all four components of the equilibrium together in a reaction vessel, and then it's going to, depending on the kinetics, it's going to proceed toward equilibrium. Well, Q tells us whether or not we're at equilibrium yet. Okay, so the nice thing is that Q expression is the same as K. Right? So if I have my generic reaction that we've been using, Q is exactly the same as K. I'll have C to the C power, D to the D power, A to the A power, and B to the B power, right? Also works for pressures. Okay, so it takes exactly the same forms as K. And what Q does is Q tells us whether the forward or back reaction is favored or if equilibrium is reached. Okay, so what we do in order to for Q to tell us this is that we compare Q to K. Okay, and we set this up alphabetically. Okay, so it's one thing to memorize Q greater than K or K greater than Q. Will tell you, if you're good at memorizing things, great. I was never good at memorizing things when I was a student. So the easiest way to not have to memorize things is to put them alphabetically. Alphabetical. Right? K comes before Q in the alphabet, right? So if you set that up correctly, then the arrow tells you which direction the reaction goes. Okay, so if I put them alphabetically, K comes before Q, and let's say that K is greater than Q. Okay, which direction is the arrow pointing? It's pointing to the right. Product favored. Or we just say that forward reaction is favored. Okay, so if I put them alphabetical, and I find that Q is greater than K, the backward reaction is favored. Okay, and if I calculate Q and find that they are equal, equilibrium has been reached. All right, so let's look at a few different scenarios for an actual reaction. Okay, so let's come back and look at our redox reaction from a while ago. That's our tin. Okay, so, and we find that we're told that the value of Kc is 1.48. Right? So, scenario 1, let's say we start with only reactants. Okay? In order to have an equilibrium, I need to have some products, right? I can't just have only reactants and have an equilibrium, right? So if I start only with reactants, the only direction that can possibly happen is forward, right? I need to make some products. Scenario 2, let's say we start with only products. And I take some copper plus and some tin 4 plus and I put them in a beaker. In order to have an equilibrium, and I need to have some of all of it, right? So if I start with only products, the only thing we can do is go backward. Okay? Scenario 3, start with some of all. Now what? Okay, so what we're going to do is write a Q expression, right? Q will tell us which direction a reaction will go in order to reach equilibrium, or if we're already at equilibrium, okay? So for this particular reaction, my Q expression looks exactly like my K expression. So I'll have copper plus squared, some tin 4 plus. They're all aqueous, so they all go in our expression. Right? So let's say that we start with .1 molar of each. Okay, I measure out 0.1 molar solutions of all 4 components, and I plunk them all down in a beaker together. All right. Will the reaction proceed forward to reach equilibrium, or will it proceed backward to reach equilibrium? All right. So I'm going to plug in 0.1 for all of my components. Okay, and we find that the answer is 1. Right? So compare Q and K. K was 1.48. Right? So if I put them alphabetically, K and Q, K is larger than Q. So reaction proceeds right. Or forward. Okay, and it will proceed in the forward direction until equilibrium is reached. Okay, so Q is a very, very useful tool for us, and it's going to be, which will be obvious here in just a little bit, because we need to know, before we try to do any calculations, we need to know which direction a reaction will go, right, based on the components that we have to start with. If we start with only reactants, no products, then it has to proceed forward. If we start with products and no reactants, it has to proceed backward. But if I start with some of all of it, I need to know which direction it will go, and Q tells us that. Okay, so now we're building our toolbox. All right, so our next step is our final topic, and that is ice tables. Okay, so ice tables are for finding equilibrium concentrations. Okay, that is very, very important. Anytime that you need to find equilibrium concentration, you will need an ice table. Okay, it's a very common bit of confusion for students. When do I need an ice table? And the answer is anytime that you have to find equilibrium concentrations. Okay, if the question says, what are the equilibrium concentrations? You need to make an ice table. Okay, now sometimes the ice tables are more complex than others, but we'll get into that. Okay, so let's talk about setting up an ice table. Okay, and why do we call it ICE? Because ICE stands for initial, change, and equilibrium. Okay, and we may even, sometimes people find it useful to put a fourth line into the ICE table for final, which tells us the actual number for the equilibrium concentration. Okay, so let's set up an ICE table for a generic reaction. And we'll do a specific one as well, so don't worry. Do a couple of specific ones. All right, so we have our generic A plus B in equilibrium with C, and we are given that K equals 4. Okay, so pretty darn generic. All right, so let's say we start with 0.1 molar of each. All right, 0.1 molar of A, 0.1 molar of B, 0.1 molar of C. Okay. So, and you know what? Actually, I'm going to do a thing here real quick, and I'm going to take out those. All right, so we just assume that our stoichiometric coefficients are all 1. Stop. Sorry, my iPad and my pencil are not agreeing with what I'm trying to do. Okay, so we start with 0.1 molar of each. So we want to decide which direction the reaction goes, right? So if I started with only products, then I know that it goes right. If I start with if I start with reactants, boy, my words are not working. If I start with only reactants, it only goes right. If I start with only products, it only goes left. But if I start with some of each, I need Q. Okay, so my Q expression, everything's 1, right? So I'll have C divided by some A and some B, right? So I'm going to plug in 0.1 for all of them. Right? And so I find out that my value of Q is 10. Okay? So K and Q, and I find that since K is only 4, Q is 10, my reaction will go left. Okay? So setting up an ICE table. An easy way to do that is to write out your equation and begin your table directly beneath it. Okay, so if I have my reaction equation, I'm going to start right below it. Okay, my concentration of A, my concentration of B, and concentration of C. Now you can do this for pressures also. Okay, I could have pressure of A, pressure of B, pressure of C. Okay. So my first line of my ice table is the initial line. Okay, and I'm told that we start with 0.1 molar of each. Okay, my change line, okay, is what is happening. How much does each concentration change? And since we don't know what that change is yet, we're just going to say X. Okay, but X is directly related to the stoichiometry, right? So remember that we had stoichiometry of 1 for each component. Okay, so I'm going to say 1x for each one. Okay, if any of my stoichiometry were 2 or 3 or more or whatever the number is, I would say 2x or 3x or 4x or whatever. Okay, now the reaction goes left. Okay, so if my reaction is going left, I'm losing some C and I'm making some A and B. Okay, so if my reaction is going left, I'm going to say minus the change in C plus the change in B plus the change in A. Okay, so minus for disappearing plus for appearing. Okay, so since the reaction is going left, minus C plus A and B. Okay, so then my equilibrium line, E for equilibrium, I'm going to combine those two lines. So I'll say 0.1 plus X, 0.1 plus X, and 0.1 minus X. Okay, so now what we're going to do, we're going to plug these into K expression. Okay, again, I apologize for my handwriting. Right, so K, let's make this a different color. So K was C over A and B, right? So if I plug these in to that expression, the value of K was 4. Right, remember, let's put this over here, K equals 4. Right, so 4 equals 0.1 minus X over 0.1 plus X times 0.1 plus X. Okay, so I've taken the equilibrium line of my ice table and plugged it into my K expression, right? And now we solve for X, right? And in this case, the math is super fun. So what we end up with, hopefully everybody remembers how to FOIL and do all this wonderful things in solving for X with a quadratic. So let's go ahead and go through some of that. I'm not going to write out every single step, but what we'll have is 4 times 0.01 plus 0.2x plus x squared equals 0.1 minus x. Right, and we rearrange the whole thing to set it equal to 0, and so we'll end up with negative 0.06 plus 1.8x plus 4x squared equals 0, and that is a quadratic. And in this case, we will need the quadratic formula. All right, so hopefully everybody remembers negative b plus or minus square root of b squared minus 4ac all over 2a equals x. Okay, and hopefully nobody's panicking at this point, but hopefully you're remembering that day when you were in algebra class and you said, when am I ever going to actually use this in real life? Well, ladies and gentlemen, here we are. All right, and so we plug everything into the quadratic and we find that there are two values for x, 0.031 and negative 0.48. Okay, we're going to find that the 0.031 is the correct value because what we're going to do now is plug x into our equilibrium line and actually get concentrations. Okay, so if I were to use the negative 0.48, I would end up with negative concentrations, right? Because what we're going to do now is we're going to come back and we're going to calculate equilibrium concentrations. Right, so this would be our final line. Right, so final, we have our, for A, 0.1 plus x. So we will say 0.1 plus 0.031 gives us 0.13. Right? Now think about this little bit right here, this 0.1 plus x. If I were to plug in negative 0.48 for x, I would end up with a negative concentration, and that is not physically possible. It can't have less than 0 of a piece of matter, right? We're not creating black holes here, right? Our concentration of B will be the same. Okay, and our concentration of C was minus X. And we'll end up with 0.069. Okay, so these are the equilibrium values. Okay, now I can check my work by calculating K from these values, right? So if I took these equilibrium concentrations and plugged them back into my K expression and solved for K, I should get 4. Okay, so that's a way that you can check your work. So let's do one that's not a generic. Okay, let's do an actual reaction. All right, so looking at our production of smog again for our equation. Equilibrium with 2NO gas. And we're given a value of Kc equals 0.10 at 2000 degrees Celsius. Okay, now the temperature really doesn't have any bearing on what we're doing here, okay? That's just a bit of factual information. So the information that you're given is that the reaction initially contains concentration of N2 equal to 0.2 molar and concentration of O2 equal to 0.2 molar. Find the equilibrium concentrations. Okay. The question says the words, find the equilibrium concentrations. That is your dead giveaway that we're going to use an ICE table. Okay, so let's take a look. So we have some N2, which is a reactant. We have some O2, which is a reactant. And initially, we don't have any NO, right? So if I have no products, only reactants, I can automatically know that reaction is going to proceed right. But I can also calculate Q as sort of a verification. So Q equals NO squared over N2 and O2, right? So initially I have 0 N2 and I have 0.2 molar of each of these. So that automatically means that Q equals 0. K is greater than Q. The reaction goes right. Okay, so even if you're not comfortable with interpreting things based on the word problem, you can always calculate Q. Okay, so the reaction goes right. Great. Okay, so let's set up our ICE table. So I have my N2, I have my O2, and I have my NO. Okay, and just because I've moved it off the screen, I'm going to bring the reaction back down and write it just above here. So we have N2 plus O2 gas, equilibrium with 2 NO gas. Kc was 0.1, right? So the reaction goes right. So that means that our N2 and our O2 are disappearing, and our NO is appearing, right? And our initial concentrations, so the initial line is 0.2 molar for each of these, and 0 for the NO. Our change line comes directly from the stoichiometry. Okay, so we have a 1, and a 2, right? So our change line, we're proceeding right, so we're losing some N2, so minus 1x. We're losing 1 O2, and we're gaining 2 NOs. Right? So now my equilibrium line will be 0.2 minus x, 0.2 minus x, and 0 plus 2x. All right? Now, we're going to take and substitute those into the K expression. Right? So our Kc expression was NO squared N2 and O2, each to the first power. Okay, so I'm going to plug these equilibrium line expressions into my K expression. So what we'll end up with is 0.10 equals 2x squared, 0.2 minus x times 0.2 minus x. Right? Now, I want to make something very, very, very clear. The quadratic equation is not the only way. Okay? We don't need the quadratic. Okay? We don't need the quadratic equation here. All right, so let me rewrite this a little bit to make it maybe a little bit more obvious what we can do with this equation to avoid using the quadratic. right? Isn't that the same thing as the Kc expression that I wrote above, right? So if I have perfect squares, which is very handy, all I have to do is take the square root of the whole thing. So I'll end up with 0.10 under the square root equals 2x over 0.2 minus x. Much, much simpler, right? Now I don't have to go through the whole quadratic equation thing. Now you can. It would be hideous and very unpleasant, but you don't have to, okay? I want to make it very, very clear to everyone. You do not have to do the quadratic equation for all of these problems. Watch for math tricks. Watch for ways that you can simplify your math, okay? Because the quadratic equation is very unpleasant, right? It's long, it's tedious, and it's fraught with possibility for mistakes, okay? So we sort of rearrange and we solve for x. So we find that x equals 0.027. Okay, so that's our change. Okay, that is not the final answer, all right? So the equilibrium concentrations okay, for N2, we have 0.2 minus 0.027. So my equilibrium concentration is 0.173 molar. Okay. Same thing for our O2. We'll have 0.2 minus 0.027, 0.173 molar. And our NO was 2 times X. Okay, so these are the equilibrium concentrations. Now let's check our work. This is a way that you can be sure that you had the correct answer. So I can plug these equilibrium concentrations into my expression and solve for K. And I'll find that this equals 0.097, which is basically the same as 0.1. Okay, which was our given value of K, right? So that means that we've done this correctly. Your equilibrium concentrations should equal K if you plug them back into the equilibrium expression. Okay, now there are times when you can simplify your math. Okay, so this is another way to avoid using the quadratic equation, all right? And it's an approximation. Okay, so when K is very small compared to the concentration, let me write out the words. When K is small compared to initial concentration, the change in equilibrium will be too small to matter. Okay, and when you can apply this this approximation is The rule of thumb here is when there is a greater than 10 to the 4 difference. Okay, 10 to the 4 difference between K and initial concentration. Okay, so let's see how this plays out. All right, so we have our dihydrogen sulfide in equilibrium with hydrogen gas and sulfur gas. We have Kc equals 1.67 times 10 to the minus 7. Okay, it's a pretty small value of K. So let's say that a 5-liter reaction vessel initially contains 0.125 moles of H2S. Find the equilibrium concentrations. Of H2 and S2. Right? You see those words, find the equilibrium concentrations? That tells you that you're going to be making an ice table. Right? Now remember that, so we're given volume and moles, and Kc is for concentration, right? C for concentration, so that means that we need things in terms of moles per liter. Right, so I can't just plug 0.025 into my 0.125 into my ice table. I need concentrations. So my concentration of H2S initially 0.0125 moles in 5 liters, or 0.5 liters, 0.025 molar. Right? And really, if I were being careful with sig figs, I should be saying just 0.03, but we're going to keep some extra digits because that's not our final answer. Okay? So we need an ice table because we're asked to find equilibrium concentrations. H2S, H2, and S2. Let's go ahead and write our equation here. And this should be 2H2S. Okay, so our initial line, we have 0.0250. And none of the H2 and none of the S2. Okay, so I could calculate a Q. I'll find that my numerator for Q will be 0. So K is 0, or excuse me, Q is 0. K is greater than Q. The reaction will go right. Additionally, the idea that I don't have any products yet guarantees that I'm going to the right. Okay, so I'm going to be losing some H2S and gaining H2 and S2. Right? So making sure we recognize there's a 2 here, a 2 here, and a 1 here. Right? So my change line, I'm losing some H2S, so I'll say minus 2x because that's what's in the stoichiometry. I'm gaining some H2, so I'll say plus 2x for the H2, and I'm gaining 1 S2. Right? So my equilibrium line will we'll say 0.025 minus 2x plus 2x and plus x. All right, so now we plug these into our K expression. So we'll say K equals 1.67 times 10 to the minus 7 equals 2x squared times x over 0.0250 minus 2x squared, right? And I wasn't careful about writing a K expression. Let's come back up here, or let's write our K expression right here. KC should be, make sure that I do this correctly, products over reactants, so I'll have H2 squared times my S2 over my H2S squared. Right? So here's where we want to look. Can I do an approximation? Right? So my initial concentration of H2S is the 0.025. Right? Compare that to K. Right? Compare the initial concentration to K. Right? We have a greater than 10 to the 4 difference. Okay, so there's something like a 10 to the 5 difference. Okay? What that allows us to do, because if I go through this arithmetic and I can solve this for x exactly as it is, it would be hideous, but I can, right? This would be a very unpleasant problem to solve. Right? Because there's a large enough difference, I can take this out and say x is small. Because K is as small as it is, the change to the 0.025 will be insignificant. Okay? I leave the other two because I'm looking at a change from 0. Right? I leave these two for the H2 and the S2 because I'm coming from 0. Right? Any change from 0 will be significant. In this case, changing from 0.025, that change will be insignificant. Right? So what that does for my equation is it allows me to rewrite it without the change minus 2x. So I'll have equals 4x to the third over 6.25 times 10 to the fourth to the minus 4. Okay? All right, because that's 0.025 squared. Right? So when I solve for x, which will be easy since I've taken that out, x equals 2.97 times 10 to the minus 4. Right? So then I would plug x into the equilibrium expressions and solve for the equilibrium concentrations. Okay? Here's how you know whether or not you're allowed to do this, right? Checking that the change is small, or we say checking that x is small, right? The way you do it is you divide x by the initial concentration. And get a percentage. Right, so in our case, x equals 2.97 times 10 to the minus 4. And the initial concentration times 100 to get a percentage, and we get 1.19%. Right? Anything less than 5% is okay. Okay, so in our case, 1.19%, we are allowed to use our approximation to simplify our math. Okay, so that does it for chapter 15. I highly recommend a lot of practice with ICE tables. We're going to use them quite a bit in the upcoming chapters, okay? Because we're going to be dealing with acid-base equilibria and buffers and all kinds of things that are going to require facility with ICE tables, okay? So enjoy, and I'll see you all soon.